The Apple M3 architecture represents Apple's third generation of desktop-class ARM-based processors designed under the Apple Silicon program. Apple announced the M3 on October 30, 2023 at its Halloween Themed Scary Fast online event, along with models of the iMac and the MacBook processors for using the M3. Unlike traditional x86 processors, the Apple M3 is based on the ARM Reduced Instruction Set Computing (RISC) philosophy, which focuses on executing simpler instructions more efficiently. The M3 is fabricated using an advanced 3nm process technology, enabling higher transistor density, lower power consumption, and improved thermal performance. This architecture is optimized for modern workloads such as multitasking, media processing, gaming, and artificial intelligence, while maintaining excellent energy efficiency. The chips are fabricated by TSMC, which is Taiwan semiconductor manufacturing company using some of the most advanced semiconductor manufacturing processes available, such as cutting-edge nanometer technology that allows higher transistor density, improved power efficiency, and better overall performance. Apple's approach strongly emphasizes vertical integration, meaning the company designs and tightly controls both the hardware and software, allowing Mac OS to be highly optimized for Apple Silicon. In addition, Apple develops custom CPU and GPU architecture specifically tailored to Mac OS rather than relying on off-the-shelf processor designs, which result in smoother system performance and better compatibility with Apple applications. This strategy enables Apple to focus on real-world workloads such as multitasking, creative applications, and everyday user experience instead of prioritizing synthetic benchmark scores, ultimately delivering faster, more efficient, and more responsive devices for end users. The primary purpose of the Apple M3 ARM architecture is to deliver high performance per watt, making it well-suited for modern computing tasks such as everyday productivity, professional creative work, machine learning, and even gaming. By focusing on energy efficiency, the M3 architecture allows Apple laptops to achieve significantly longer battery life while still maintaining strong performance levels, reducing the need to compromise between power and portability. At the same time, the architecture is designed for high-performance computing, offering faster and more responsive CPU and GPU performance for demanding applications such as video editing, 3D rendering, and software development. The unified memory architecture further enhances efficiency by enabling the CPU, GPU, and neural engine to share the same memory pool, which reduces data duplication, lowers latency, and improves overall system responsiveness. Additionally, the M3 architecture includes advanced graphics and artificial intelligence capabilities, such as hardware-accelerated ray tracing and a powerful neural engine, allowing the chip to efficiently handle machine learning tasks, advanced visual effects, and modern graphical workloads with improved speed and realism.
Next, let's dive into section 2.1, CPU organization. To understand how this processor delivers such high performance, we need to look under the hood at its architecture and how it actually handles tasks. First, let's talk about the core design philosophy. This chip is built on a RISC foundation, specifically using the ARM v9e architecture. For those who aren't familiar, RISC stands for Reduced Instruction Set Computer. Unlike older, more complex architectures, RISC focuses on smaller, highly optimized instructions. This allows the CPU to operate with maximum power efficiency without sacrificing speed. Supporting this architecture is the cutting-edge 3nm process. This is actually the world's first PC chip to use 3nm technology. By shrinking the components down to this scale, we can pack a much higher transistor density into the same physical space. In simple terms, more transistors mean more processing power, while using less energy and generating less heat. How does it actually manage the work? That comes down to the control unit and execution logic. Instead of just following a simple list of tasks in the order they arrive, this chip uses out-of-order execution. It analyzes the workload and processes instructions in the most efficient order possible. If one task is stuck waiting for the data, the chip doesn't stop. It jumps to another task to keep things moving. This is made possible by a large instruction window. You can think of this as the chip's look-ahead ability. It can see a huge queue of upcoming tasks all at once, which allows it to keep every processing lane busy at all times. This prevents bottleneck and ensures the CPU is never just sitting idle. Within those performance cores, Apple used what's called wide execution. These cores feature several wide ALUs that can handle simultaneous complex maths, covering both integer and floating point operations at the same time. This is essentially like adding more lanes to a tool booth to process more cores simultaneously. Of course, all that power is useless if the data can't get where it needs to go. That's where the communication and data bus come in. The system fabric acts as a high bandwidth internal highway. It's designed specifically to remove the traditional bottlenecks that usually slow down data transfers between different parts of the chip. To keep the workflow smooth, the chip uses register renaming. This is a clever trick that prevents data hazards by mapping software register onto a much larger pool of physical register. It basically allows the CPU to juggle multiple tasks without them tripping over each other's data. Finally, Apple has unified memory access. All units share a massive 100 GB per second bandwidth. Because every part of the chip has instant access to this memory pool, Apple effectively eliminates weak states. This processor never has to sit around waiting for the data to arrive from a slow memory bus. With the Mac units and the data highways working in perfect sync, the CPU can maintain incredible speed under heavy workloads. Moving on to section 2.2, let's look at the register set, the CPU's most immediate storage. First, we have the general purpose register, labeled X0 through X30. Think of this as the workhorses. There are 31 of the 64-bit registers, and they are used for everything from integer maths to storing memory addresses. Some of these have very specific role. X30, known as the linked register, is used to remember exactly where to return after a function call finishes. Meanwhile, X0 through X7 are primarily used to pass arguments or inputs into function and receive the return values back. Finally, we have the control and status registers, which act as the management team for the CPU. The program counter is the manager. It always points to the very next instruction in line. The status register is the observer. It records the result of the last operation, noting if it was negative, zero, had a carry, or an overflow. The stack pointer manages the stack, keeping track of local temporary data so nothing gets lost during complex operation. Understanding this register is key because they are the interface between the software instruction and the high-quality speed hardware we discussed earlier. Finally, for the most demanding tasks, we have the floating point and SIMD registers. These 32 registers are 128-bit high-capacity storage, often referred as the media engine. They utilizes SIMD, which stands for Single Instruction Multiple Data. This allows the chip to process multiple pieces of information, like pixels in a 4K video or samples in an audio file in one single clock cycle. This optimization is exactly why this architecture excels at video rendering, AI workloads, and complex 3D graphics. To understand why the M3 chip is so fast, we first have to look at how the brain of the computer talks to the rest of the body. In traditional system, we use a system bus, a communication pathway that connects the CPU to memory and input-output devices. In the M3 architecture, this bus is highly optimized. Think of it as a multi-lane highway where data doesn't just travel fast, but it travels intelligently. It is composed of three main parts. The address bus, this tells the system where data is going. The data bus, this carries the actual cargo or information. The control bus, this acts like a traffic controller, signaling whether we are reading or writing data. Now, let's look at the biggest game changer in Apple's ARM architecture, unified memory. In a traditional PC, you have two separate buckets of memory. You have RAM for your CPU and VRAM for your GPU. If the CPU finishes a task and needs the GPU to render it, the data has to be copied from one bucket to the other across a relatively slow interface. This creates a bottleneck. In the M3, Apple removed those walls. They use a single pool of memory because the CPU, GPU, and neural engine all sit on the same chip. They all look at the same memory pool. No copying, no moving, just instant access. This is why a Mac with 8 GB of memory can often feel as fast as a PC with 16 GB. Moving deeper into the architecture, let's talk about the three-level cache hierarchy. This is designed to keep data as close to the processor as possible to avoid asking the main RAM for info constantly. L1 cache. This is a private and ultra-fast, built directly into each core for zero delay access. L2 cache. This is a larger pool shared within a core cluster, acting as a high-speed buffer. System-level cache. This is a massive L3-style cache that connects to the CPU, GPU, and neural engine together. To keep this efficient, we use set associative mapping. This is the middle ground of memory organization, faster than fully associative, but more flexible than direct mapping. It reduces cache conflicts and ensures our data hit rate stays above 90%. Finally, we have the M3's secret weapon, dynamic caching. In the old wave of doing things, GPUs would reserve a huge block of memory at the start of a task, even if they didn't use it all, which wasted space. The M3 way is different. It allocates memory in real time, based on the exact needs of each instruction. This leads much higher GPU utilization, allowing more tasks to run in parallel. This is exactly why the M3 has such a significant lead in professional 3D rendering and high-end gaming. At the core of Apple M3 is its memory hierarchy, which is designed to minimize latency and keep the CPU pipelines busy. Starting from the fastest level, we have registers, followed by cache, then main memory, and finally secondary storage like SSDs. What makes Apple M3 special here is its integrated or unified memory architecture, where RAM is physically packaged close to the chip. This drastically shortens the electrical distance data has to travel, which means faster access and better energy efficiency. In practice, data flows from the SSD into unified memory, then into caches, and finally into registers right before execution. The goal of this hierarchy is simple: make sure the CPU is never waiting for data. By feeding the execution pipelines continuously, Apple reduces idle cycles and improves overall performance per watt. Now, let's look at how these components communicate using the structured bus system. The bus is made up of three main types of line. Address lines specify where the data should go or come from. Data lines carry the actual bits being transferred. And control lines coordinate everything by managing read and write signals and ensuring proper synchronization between the CPU, memory, and I/O devices. Together, these lines allow smooth and orderly communication across the entire system on chip. Finally, we have Direct Memory Access, or DMA, which plays a critical role in high-performance systems like the Apple M3. Instead of forcing the CPU to manage every data transfer, dedicated I/O controllers handle large data movement on their own. This allows data to move directly from devices, such as storage, networking, or peripherals, straight into RAM without constant CPU involvement. The benefit here is huge. For demanding tasks like 8K video editing, fast file transfers, or high-speed networking, DMA prevents the CPU from being overwhelmed by simple data movement. As a result, the CPU can focus on computation while the rest of the system handles data flow efficiently. Next, let's jump into the hybrid core design used in the Apple M3 ARM architecture, which is a great example of heterogeneous computing. Instead of using a set of identical CPU cores, the Apple M3 combines two different types: performance cores or P cores and efficiency cores or E cores. This dual core strategy allows the system to adapt to what you're doing at any moment, rather than wasting power by running everything at full speed all the time. The operating system plays a key role here through smart task allocation. Using mechanisms like quality service or QoS, the system automatically decides which type of core is best suited for each task. Heavy workloads are sent to powerful cores, while lighter background tasks are handled more efficiently elsewhere. Starting with the performance core, these are essentially the muscle of the chip. They are designed for high-intensity tasks such as 3D rendering, software development, and gaming. Architecturally, P-cores feature wider execution pipelines and larger L2 caches, allowing them to process more instructions at once. On the Apple M3, these cores can reach clock speed of around 4.05 GHz, delivering noticeable performance gain compared to the previous generation. On the other side, we have the efficiency cores, which handle the majority of everyday tasks. Things like email, web browsing, Wi-Fi activity, and background syncing usually runs here. This core consumes only a fraction of the power of P-cores and are optimized to stay cool and silent. While their clock speed are lower, up to about 2.75 GHz, they are extremely efficient for continuous, lightweight workloads. Tying everything together is the power management controller. You can think of it as a real-time traffic director. It constantly monitors system activity and moves tasks between P-cores and E-core clusters within milliseconds. This dynamic balancing ensures that performance is available when needed, but power isn't wasted when it's not. The result is exceptional performance per watt. By intelligently distributing workloads, the Apple M3 is able to deliver performance comparable to high-end PCs, while using only a fraction of the power. This hybrid core design is one of the key reasons Apple Silicon stand out in both performance and energy efficiency. Lastly, let's look into the specialized accelerator in the Apple M3 ARM architecture, known as the Neural Engine. This is Apple's purpose-built hardware for artificial intelligence and machine learning tasks. The M3 includes a 16-core neural processing unit, or NPU, that operates independently from both the CPU and the GPU. Instead of using general-purpose cores, the Neural Engine is optimized specifically for AI workloads. In terms of raw capability, the Neural Engine delivers massive throughput, capable of performing up to 18 trillion operations per second. Its internal spatial architecture is designed around matrix multiplications, which are the fundamental mathematical operations behind neural networks. This makes it extremely efficient for tasks like image recognition, speech processing, and real-time analysis. One of the biggest advantages of the Neural Engine is efficiency. AI tasks such as Siri requests, Face ID, or background photo effects can be handled using far less power than if those same tasks were run on the GPU. By offloading AI workloads to the Neural Engine, the system remains responsive because the main CPU cores are freed up to handle other user tasks. Another key benefit is privacy. Since the Neural Engine enables on-device AI, sensitive data like voice input and photos can be processed locally without needing to be sent to the cloud. This aligns closely with Apple's privacy-first design philosophy. Finally, the Neural Engine is tightly integrated into Apple's unified memory architecture. It sits on the same high-speed system fabric as the CPU and GPU, giving it instant access to shared memory. This enables zero-copy data access, meaning the Neural Engine can analyze photos or video frames immediately after capture without wasting time or energy moving data between separate memory pools.
Hi, my name is Luzma, and in this part, I'll be talking about the instruction cycle of the Apple M3. At the heart of program execution is the instruction cycle, commonly known as the fetch, decode, and execute cycle. This cycle describes the fundamental steps the CPU follows to process instructions. First, an instruction is fetched from memory, then decoded to determine the required operation, and finally executed to produce a result. It will then be stored, and the cycle will repeat as it goes back into fetch. In modern processors like the Apple M3, this cycle is highly optimized. Rather than processing one instruction at a time, the CPU can work on multiple instructions simultaneously, improving throughput, meaning more instructions can be completed per unit time while keeping internal resources fully utilized. The fetch phase retrieves the next instructions or instructions from memory. During this stage, the program counter or PC holds the address of the next instruction in the program. The instruction is typically fetched from the L1 instruction cache, which provides fast access and stored in an instruction buffer. After the instruction is fetched, the PC is updated to point to the next address. To reduce delays, Apple Silicon processors use branch prediction, which speculatively determines the most likely execution path so that instruction fetching can continue without interruption. Modern ARM-based design, including Apple M3, can fetch multiple instructions per cycle, helping to keep the pipeline full and reducing performance stalls. In the decode phase, the processor interprets the fetch instructions. EOP code is examined to determine the operation, while source operands and destination registers are identified. The instructions is then translated into internal operations suitable for the CPU's execution units. Advanced techniques are used at this stage to improve performance. Register renaming eliminates false data dependencies, and dependency checking ensures instructions only execute when the required operand are ready. Decoded instructions are placed into an instruction scheduling window, allowing the processors to dynamically reorder instructions and support out-of-order execution. The execute phase performs the operations specified by the instructions. Instructions are issued to appropriate execution units such as integer ALUs, floating point units, vector units, or load store units. In the Apple M3, superscalar execution allows for multiple instructions to execute in parallel across different units. Results can be forwarded directly to dependent instructions to reduce delays. Once execution is complete, instructions are committed in program order, ensuring correct programming behavior. Overall, features such as pipelining, out-of-order execution, and hierarchical caching allow the Apple M3 to efficiently extend the basic instruction cycle, delivering high performance while maintaining power efficiency.
The Apple M3 chip delivers a significant performance improvement over earlier generation, offering up to 35% faster CPU performance and up to 65% faster GPU performance compared to the M1, which results in quicker app launches, smoother multitasking, and faster processing for remaining workloads. One of its major upgrades is support for hardware-accelerated ray tracing, which greatly enhances lighting, reflection, and visual realism, making it especially beneficial for graphic designers, 3D artists, and gamers. The introduction of dynamic caching further improves graphics efficiency by allowing the GPU to allocate memory dynamically based on workload needs, reducing waste of resources and improving overall performance. Additionally, the M3 supports up to 24 GB of unified memory with increased memory bandwidth, enabling faster data access and smoother performance when handling large files, complex applications, and intensive creative or professional tasks. Despite their many advantages, ARM processors also have some limitations. One concern is limited performance, as ARM-based processors may not always match the raw power of some high-end processors designed for extremely demanding workloads, such as having heavy scientific computing or specialized professional applications. Another challenge is software compatibility, since some programs are not fully optimized or natively support on ARM architecture, which can restrict the range of applications available or require emulation that may reduce performance. Additionally, multitasking efficiency can be a limitation in certain scenarios, as ARM processor may not handle multiple highly demanding applications as effectively as other processors in architectures, potentially impacting performance when running several intensive tasks simultaneously. The Apple M3 chip represents a clear advancement over the Apple M2, mainly due to improvement in manufacturing technology, performance, and power efficiency. Firstly, the M3 is built using a 3nm fabrication process, while the M2 uses a 5nm process. This new technology allows Apple to place more transistors onto the chip, resulting in better performance, improved thermal management, and greater energy efficiency. As a result, the M3 can perform more tasks at higher speed while generating less heat. In terms of performance, the M3 is noticeably faster than the M2 in both CPU and GPU tasks. It offers approximately 15 until 17% better CPU performance in everyday computing activities such as web browsing, document editing, and multitasking. Additionally, the GPU performance is improved by around 15 until 20%, leading to smoother graphics, faster rendering times, and better support for creative applications and light gaming. This improvement contributes to quicker application launches, more responsive system performance, and an overall smoother user experience compared to the M2. Finally, the M3 delivers improved power efficiency thanks to its 3nm design. This allows the chip to achieve higher performance levels without significantly increasing power consumption, which is especially important for portable devices like MacBooks. As a result, Macs equipped with the M3 often provide longer battery life than those using the M2, even when performing demanding tasks. Overall, the Apple III offers a more powerful, efficient, and feature-rich solution compared to the M2, making it a strong upgrade for users who value performance and battery longevity. The Apple M3 architecture is well suited for mobile and portable devices such as laptops due to its strong power efficiency and thermal performance. It is also effective for desktop and creative workloads, including video editing, graphic design, and software development, where fast CPU and GPU performance are important. However, it is less suitable for embedded systems or IoT applications because it is designed for high-performance consumer devices rather than low-cost on real-time environments. Additionally, the M3 is not ideal for server use due to limited scalability, enterprise features, and restrictions within Apple's ecosystem.
In conclusion, the study examined the Apple M3 architecture from a computer architecture perspective, focusing on structural design, instruction cycle, memory hierarchy, and overall system integration. The findings show that the M3 is a highly optimized ARM-based system on a chip that prioritizes performance per watt through architectural efficiency and advanced semiconductor technology. Features such as the hyper-performance and efficiency core design, out-of-order and superscalar execution, and deep cache hierarchy enable efficient instruction processing with low power consumption. The unified memory architecture reduces data movement and latency by allowing CPU, GPU, and neural engine to share a single high-speed memory pool. Specialized accelerators including 16-core neural engine and integrated GPU dynamic caching further enhances graphics and multimedia performance. Overall, the Apple M3 delivers strong computational performance with excellent energy efficiency, making it well suited for modern laptops and compact desktops, while also illustrating the growing importance of unified memory, hardware acceleration, and energy-aware processor design.